Hi, we are group 3 for the Stat 512 final project. So our study was around climate change and what different factors may influence the average temperature within the US. This study was relevant due to the current state of the world and how global warming is a big issue, and it would be interesting to see what different factors may be significant in a temperature increase. The first question was how do weather events impact the average monthly temperature within the US, and more specifically, what is the impact of droughts and rainfall? This question was based on literature that suggested that droughts would be a strong predictor of a change in temperature or an increase in temperature. And I was also interested in how rainfall may be connected, given droughts and rainfall are kind of opposite events. So the first question was, do drought levels have a significant impact? And then the second question was, do drought and rainfall levels have a significant impact? So, and then I've got my hypotheses on the screen as well. So beta 2 is 0 for null, beta 2 non-zero for the alternate for the first question. And then the second question, beta 2 and beta 3 equals 0, alternate beta 2 or beta 3 non-zero. So then I proceeded with preliminary analysis of the data. This indicated that X1, X3, and X4 were significant. So that's fires, rainfall, and tornadoes. And then also showed an R squared of 0.59, which is a relatively strong model. This was surprising that X2, being droughts, was not a strong predictor, as this kind of went against literature. Next step was to go through some diagnostics. I used a few different tests to check for multicollinearity, for normality, and constant variance. And all the tests showed that none of these assumptions were violated. So then I proceeded on to check for influenza points. So I used a Cook's distance test, a DF fits test, and also a DF betas test. Based on these findings, observations 26 and 32 were very likely to be outlier points, as well as observation number 1, as these points appeared in multiple tests. So I proceeded to remedial measures. As mentioned, there were no issues with variance, multicollinearity, or normality, but there were some outliers. So I removed these 3 points, and this improved the model as the R square value went from 0.59 to 0.62, and the AIC value also lowered. This indicated an improved model. I also did try a robust model, but instead of removing influential points, but this had a higher standard error, so it was not used. I also made sure to validate the model with the k-fold procedure, and we can see from the RMSE values and the R squared values that the model was valid. Next, the final step was to look at the hypothesis testing. I just used ANOVA testing for this. So for the first question, we can see the p-value is 0.7392, which is larger than 0.05, so we would not reject the null and make a conclusion that droughts were not significant to the average temperature. Question 2, we can see that the p-value is significantly smaller, 8.8 times 10 to the negative 5, which is clearly less than 0.05. So we reject the null and conclude that droughts and rainfall were significant to the average temperature. This was a surprising result, as again, literature indicated that droughts would be the strongest predictor, and rainfall may not be as influential, but it kind of appeared to be the opposite in our data set that we analyzed. This probably points to a couple potential limitations, such as a small sample size, and also just the way the data was presented for drought specifically may not have been too specific, but it was an interesting result.
The second question is there a relationship between national greenhouse gas emissions and the changes in average national temperature within the last 20 years? The Y variable, the dependent variable, is changes in average national temperature annually, while the independent variables are annual CO2 emissions, annual methane emissions, annual nitrous oxide emissions, and annual fossil fuel consumption. Carbon emissions are released in nearly every industrialized process known to man, which is why they impact our lives and play a big role in the things that we care about in terms of climate change. So our hypotheses are, the null hypothesis is that the effects of carbon dioxide and fossil fuel consumption on annual temperature change are equivalent. The alternate hypothesis is that they are not. For our initial model building, X3 appears significant due to a small p-value. In our initial model diagnostics, we checked for things such as normality of residuals and constant variance, which you can see here. Through the Shapiro-Wilk normality test, we saw that the residuals are normal, and through the residual plot, we were able to see that there was constant variance. After we cleared those, we performed some more advanced model diagnostics, such as the added variable plot, in order to display marginal effect, as well as multicollinearity through VIF and tolerance values. Through both of these diagnostics, we were able to see that X2 may be problematic in terms of multicollinearity. We also performed Cook's D, DF fits, and DF betas, as well as checking for outliers of X through hat values and outliers of Y through R student values. Through these measures, we were able to identify case 25, 13, and 33 as potentially problematic points. In order to alleviate some of these issues, we performed ridge regression. After performing ridge regression, we redid the VIF values, and still we saw that X2 was problematic and indicating high multicollinearity. After this, we performed model selection in R, which led to the removal of predictor 2 in the model. We also performed robust regression, and after performing robust regression, all the VIF values appear to be close to 1, indicating no multicollinearity. X1, X3, and X4 appear to have a significant relationship with Y, and they passed the leverage test. As for predictive power, R squared was equal to 34.2%, meaning the model explains around 34% of variance. Overfitting does not appear to be a concern, and the cross-validated RMSE of 1.046 and the manual RMSE of 0.983 appear to be pretty close together in value. The annual data may have decreased the effectiveness of this model. In terms of hypotheses testing, we were able to see that we could reject the null hypotheses because the p-value was less than 0.05. Rejecting the null hypotheses means that the impact of carbon dioxide is not equal to the impact of fossil fuel consumption. This leads us to believe that other factors other than fossil fuels are leading to large roles in the release of carbon dioxide.
I investigated which energy production source contributes more to rising average temperatures, oil production or coal consumption. The response variable is the average temperature in the United States. The predictor variables include oil production, annual electricity consumption, share of primary energy consumption that comes from fossil fuel in the United States, share of primary energy consumption that comes from renewables, and coal consumption. The null hypothesis includes oil production and coal consumption have the same effect on average temperature in the United States. Beta 1 equals beta 5. The alternate hypothesis includes oil production and coal consumption have different effects on the average temperature in the United States. Beta 1 is not equal to beta 5. In the preliminary analysis, I conducted the Shapiro-Wilk and Bush-Pagan tests, and both confirmed that the model residuals were normally distributed and had constant variance. In the advanced diagnostics, the VIF value showed serious multicollinearity among predictors. Influential points, especially 28, 48, 55, and 56, were identified using studentized residuals, Cook's distance, hat values, different in fit, and different in beta values. The added variable plots showed weak but generally linear relationships, which likely is impacted by multicollinearity. The first remedial measure I took was I first applied ridge regression, which stabilized the coefficients and decreased the VIF values. I then used robust regression to reduce the impact of outliers, lowering the residual standard error from 1.004 to 0.8549, which indicates a better fit. While Model 3 had the best statistical performance, it only included 3 predictors. I chose Model 4 for hypothesis testing because it kept more predictors while maintaining strong SSE, adjusted R-squared, CP, AIC, and PRESS values. In the hypothesis testing, I used the full model and the reduced model. Since p-value is greater than 0.05, we failed to reject the null hypothesis, meaning both oil production and coal consumption likely have similar effects on temperature, which is consistent with both being major fossil fuel sources. This investigation aimed to explore whether there was a meaningful distinction, but the data did not support it. I then performed k-fold cross-validation, which showed that the reduced model slightly outperformed the full model with higher R-squared values. However, the predictive power is limited due to using annual data and fewer predictors. Future improvements could involve adding seasonal or monthly data, expanding variables, and regularly updating the model to reflect changing energy trends.
Does the monthly manufacturing and transportation construction spending significantly improve the model predicting the monthly average temperature? I chose the manufacturing and transportation and spending variables to focus on since those are the most vital to the global warming crisis. The range of monthly average temperature ranges from 2002 to 2016. The initial model is the normal y equals x1 plus x2 plus x3 plus x4, or the simple model. However, it's 0.008539 for r squared, and so which suggests a very bad fit, which can be shown through the normal QQ plot. This plot does not suggest a normal distribution as well as the Shapiro-Wilk normality test. So we need to do the transformation or a polynomial model. So we'll do the transformation first, and we'll attempt to use box Cox, get a lambda of 0.7576 at the top of this curve. However, using this transformation in y to the lambda, we'll get a QQ plot that's not normal either. So we'll have to resort to the cubic polynomial model, which will result in a normal distribution. And we can begin looking at the Cook's distance for this model, and a few values that seem like outliers are 1, 119, and 167. Studentized residuals. Initially, the residuals are not distributed with equal variance, so we run one iteration of WLS. So the model has a p-value of 1, so now everything's more spread out. In DF betas, there are many variables to consider due to the nature of the cubic model with its interactions. We have a large sample size from 2002 to 2016, and it's monthly, so it's around 177 samples. So 2 over square root of 177 is around 0.15, and many values fall above this 0.15 range, like here, here, and here. And we can list them off. And so, since there's so many influential values, it is best to use a robust model. Comparing the original model to the new robust model, the original model has 11.38 standard error compared to the 9.7 standard error of the new robust model. VIF values are really high, which suggests very high multicollinearity. So we can attempt to use ridge regression. However, ridge regression will result in a lambda of 0, and so we'll proceed with only the robust model and our fitted WLS. The hypothesis test itself, we want to test if B1 equals B4 equals 0, which represent our manufacturing and transportation variables, respectively. Our reduced model does not include any x1 or x4 and their factors. Our full model is our alternative, and we reject this null hypothesis since our p-value is very low. There is significant evidence that manufacturing spending and transportation spending are vital to predicting the monthly average temperature from 2002 to 2016. Cross-validation wise, the results suggest that the full model performed better than the reduced model, supporting the hypothesis test since it has a larger R squared value than the reduced model. In conclusion, there is a significant evidence that deconstruction spending on manufacturing and transportation spend are not negligible in the polynomial prediction. It is a weaker correlation, and as you can see here, however, and also the multicollinearity, the only thing we did to account for it is scaling and subtracting the mean dividing by the standard deviation. And even so, seeing that these two variables play a significant role in the full model itself.
I will be presenting research question 5. My question is, does the ruling party of the U.S. House, Senate, presidency, and any combination thereof influence average U.S. temperature in the month of July? My data set comprise of annual temperature in the month of July from years 1895 through 2024. My predictors are year, political party in control of the House, Senate, presidency, or president affiliation with party, and government unity. That is unified or divided. My null hypothesis is control of aspects or combinations of aspects of the U.S. government by either party do not statistically impact average annual temperature. The alternative hypothesis would be that control of aspects or combination of aspects by either U.S. Political party does impact average annual temperature. My diagnostics showed that there is no issue in linearity, normality, or any extreme influential points. A VIF test showed that there was some significant collinearity between House and Senate, but this is to be expected as both chambers have similar rows, and when one party controls one, they usually control the other. So I decided to leave this both predictors in my model. Quick look at the data shows a constant uptrend in temperature over years, and just looking at the average temperature based on single political predictors, no real differences can be seen. Testing using one-way ANOVA to test the impact of single variables on the impact of temperature showed that there was no statistically significant correlation between control by one party or the other on temperature. Multiple regression test showed that the only real impact was temperature. Or I'm sorry, the only real impact was year on temperature. However, two-way ANOVAs showed that when one party controlled both the House and the Senate, that this was significant. And however, further investigation shows that when the Republicans control only the House, the Democrats control the Senate, that there is on average a increase of temperature of 1.5. But when the Republicans control both the House and the Senate, that there is a decrease of 1.7, which these may indicate a strong correlation between Democratic control of the Senate and temperature, or it may be in a issue with the model. To investigate this further, I developed a new model which controlled the year and investigate further, and this showed that no single variable and the interaction between House and Senate were not statistically significant when controlled for year. This led to a new model, this led to the conclusion that the full model with the political predictors were not needed, and that only year was significant in predicting temperature. However, with this new model where year is controlled, the unity of the government is still statistically significant with years that have average, with years that have a unified government on average are 0.45 degrees warmer. This led to the conclusion of rejecting the null hypothesis, as the interaction between year and party unity does statistically impact average temperature, albeit by a very small effect size, and the R square was very low. This leads to area of improvement for the assignment as a whole. One limitation was the lack of consistency between data sets between different group members, and also the complexity of studying temperature as a characteristic.